Me again. I'm wearing the same clothes because I'm doing these all in order here. So, me again. Um, Last time we did a Taylor series, we did it for e to the x. And the time before that, we did a McLaurin series for sine x and for cosine 2x. So, what we did with all of those is we said, what if I want to model a function that already has its own function? But one of the things that I've tried to do with you guys throughout the year is show you that math doesn't have a plan. Okay? If it did, you know what? Perfect example. Oh, I love using math in real life, even though when it's right now, and now I'm sad. Um, what I'm about to say is making me happy and sad at the same time. If the coronavirus pandemic had an equation, we would know how long school would be closed for. The president wouldn't have to guess when to reopen the country. Governor Cuomo wouldn't need to guess when to do what. If we had a coronavirus equation, we would know when the peaks were going to occur. But guess what, guys? We don't know that. All we know about are rates of change at specific points in time. Fast forward to what does that have to do with series, Mrs. Vibber? Well, aren't derivatives just rates of change? Yes, yes, they are. So you can also use Taylor series for a function that doesn't have a name, where all you have are data points. So let's say that you know on day 3 of said virus spread, one, we'll say, 1,000 people had the virus. And also on day 3, you know that people are being infected at a rate of 4,000 people per day. Now, this is scary. So now I don't want to say that anymore. But my point is, we have now data instead of an equation. So we're going to use the data to create a polynomial equation so that we can extend the curve and see where it's headed. And if you've been watching any of the news right now, that's what they're doing. They're just plotting points and fitting the curve to it. Okay. So, if there was ever a point for me to say, this is important, it's right now. Okay. Now, don't get scared, all that. If you're like, Mrs. Weber, seriously, I turned off CNN a while ago. I don't want to hear about it. I'm done now. My point is, though, math isn't always done to model other math that already exists. Sometimes math is done because I don't have a function yet and I need to make one. Okay, so that's what we're going to do right now. So it says f is a function, but I don't know what it is, that has derivatives of all orders for all real numbers. And now I know that f of 3 is 1, f prime of 3 is 4, f double prime of 3 is 6, and f triple prime of 3 is 12. What that tells me is that f contains the point 31. At the point 31, it has a slope of 4. At the point 31, its second derivative is positive, which means it's concave up, which means it's getting steeper and increasing. And the third derivative is also positive, which means that technically the second derivative is increasing. And so if the second derivative is increasing, how do I want to say this? It's getting more concave, I guess is the way that I would say that. But that's probably not perfect. So if anybody's watching this who has a better way to say that, please let me know. I want to write an equation though, because all this is rates of change. I want to know, what does it look like? So bloop, what I'm going to do here is say, you know what? In those previous questions, we said that all of these things become my numerators. So if I want a third degree Taylor for f, I could say f of x can be approximated by doing 1 over 0 factorial x minus 3 to the 0, because I'm centered at 3, and then plus 4 over 1 factorial x minus 3 to the first, plus 6 over 2 factorial x minus 3 squared, plus 12 over 3 factorial x minus 3 cubed. And there's my third order Taylor polynomial for f at x equals 3. I mean, that's it. That's it right there. So before I even go on, I'm going to quickly go to, you heard it, you guessed it, Desmos. So 1, 4, 6, and 12, right? 1, 4, 6, and 12. Yes. So I don't have a function to model it against, so I'm just creating this. So I have, where is it? 1 is just 1. Why are you not jumping? 1, and then 4 over 1 factorial x minus 3 to the first, 6 over 2 factorial, which is just 2, x minus 3 squared, and 12 over 3 factorial, which by the way is 6, x minus 3 cubed. Okay, and this function models another function, but what I know about it is it models it near 3. So 1, 2, 3, my modeling is really centered around the point 3, 1. Okay, so I can trust this graph to be kind of reasonable, like on this window, maybe not much further. I don't want to extrapolate too far. Okay. All right, so there's my graph. And then it says use the third order to approximate f of 3.2. So I'm going to plug in 3.2 for all of those x's. So f of 3.2 is going to be approximately, well, this is really just 1. And then when I plug 3.2 in for x, all of these parentheses are going to be point 0.2s. So I'm going to have 4 times point 0.2 to the first plus 6 halves point 0.2 squared plus 12 sixth point 0.2 cubed. And so f of 3.2, let me just get a value here so we can talk about it. Do, 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 do. Hmm. Yay. So if I want that, now my little camera's in the way. How do I get rid of this? Oh, I can move it. That's helpful. So if I want to figure out what that is, I have 1 plus 4 times point 0.2 plus 3 times point 0.2 squared and plus, what's that going to be? 2 times point 0.2 cubed. 2 times point 0.2 cubed. And so I estimate that by the time I get from 3 to 3.2, y is going to go from 1 to 1.936. Okay, cool. All right, what does it say next? It says write the second order Taylor polynomial for f prime at x equals 3 and use it to approximate f prime of 2.7. Well, do you guys remember when we did those geometric series? Once we had a geometric series, if I wanted the derivative, I just took the derivative because once you have a series, you have a polynomial. And if you have a polynomial, those are the easiest derivatives to take. So for part B here, if I want f prime, let me not use green. Let me go red. All right, so for part B, I'm going to take this f function and take its derivative. So f prime is going to be, well, the derivative of this first term, which is just a 1, would be 0. The derivative of the next term is just going to be 4. The derivative of the squared term is going to be 12 over 2 factorial x minus 3 to the first. And then 36 over 3 factorial x minus 3 squared. So there's the second order Taylor. Second order means second degree, by the way, for f prime. Ooh, I'm going to get points off. This isn't f prime exactly. It's approximately f prime. So I got to use a squiggle there. So there's a second order Taylor, which means f prime of 2.7 is going to be 4 plus 6 times 0.3. Oh, wait, negative 0.3, because 2.7 minus 3. Plus 36 divided by 6 would be 6 of negative 0.3 squared. So 4 minus 0.18 and plus 6 times negative 3 squared. 6. Oops. I know I didn't need the negative. I don't know why I typed it. 4.36. Okay. Then it says, does the linearization of f underestimate or overestimate the values of f near x equals 3? You need to be able to say, wait, 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 linearization means something fancier in calculus. Linearization means tangent line. And if I want the tangent line for f, the tangent line for f is the first degree Tailor. So the tangent line for f would be these terms. All right, so my linearization for this next part, for part C, would be f of x can be approximated using the tangent line, 1 plus 4 times x minus 3 to the first. But it says, is that going to be an overestimate or an underestimate? So we've got to now think about, wait a minute, tangent line, overestimate, underestimate. When I draw tangent lines to things, they are an underestimate to a function if that function is, yes, you said it, concave up. And tangent lines are an overestimate if the function is, yes, you're right, concave down. So I need to know, is this function concave up or concave down? Concavity of a function is defined using the sign of its second derivative. Hey, they had a list of derivative values up here, didn't they? There's my second derivative. F double prime of 3 is 6. 6 is a positive number. So then I would say that since f double prime of 3 is positive, f is concave down, making the tangent line lie above, therefore overestimate. I should say above f, therefore it's an overestimate. All right. Ta-da! Okay, that one took me longer than I thought, but I'm still going to go on and do the next one. So bear with me, and the next one's coming now. Bloop. All right. So for this next thing, it says, oh, they gave me the polynomial, and then they ask me questions about it. So now we have to work backwards. So it says, let P4 of x be the Taylor polynomial of order 4 for the function f at x equals 4. Assume f has derivatives of all orders for all real numbers. A says find f of 4 and f triple prime of 4. B, write the second order Taylor for the derivative. C, write the fourth order Taylor for the specific antiderivative centered at 4. And D, can the exact value of f of 3 be determined from the information given? Justify your answer. Okay, I got to work backwards now. So what we need to realize here is that these all came from fractions. Okay, so what I know based on this is that I know that 7, and I'm going to try to make this as neat as I can, 7 really came from the 0th derivative at 4 over 0 factorial x to the 0. Well, that just really means that 7 equals f of 4. Cool. Now let's look at the next value, negative 3. Negative 3 is in the position of the first derivative over 1 factorial x minus 4 to the first. I should have said x minus 4 to the 0. Okay, well, I ignored this because I'm only looking at the coefficient, so I'm going to ignore it now, which means if I take this and solve for the numerator, negative 3 is f prime of 4. Positive 5. 5 is in the position of the second derivative over 2 factorial, which means f double prime of 4 is 5 times 2 factorial, which is 10. Now they wanted f of 4. Okay, I have that. That's 7. Cool. And they want f triple prime of 4. Okay, so I got to go one more out. So if I want f triple prime, it's going to come from the coefficient of x cubed, or in this case, x minus 4 cubed. So if I take that coefficient, -2 is in the position of the third derivative over 3 factorial. So -2 times 3 factorial is the third derivative. And that's -2 times 6, which is -12. And if you're asking yourself, hey, Mrs. Weber, can I like notice a pattern here? Yes, you can notice a pattern. So instead of doing all the work, let's pretend I also asked for, hey, what's the fourth derivative at 4? The fourth derivative at 4 is the coefficient times 4 factorial. So that'd be 6 times 4 factorial, which is 6 times 4 times 3 times 2 times 1, which is 24. 24 times 3 is 72. 72 times 2 is 144, if I can math correctly today. Okay. Then part B says write the second order Taylor approximation for f prime. Use it to approximate f prime of 4.3. Easy. If I want to take a derivative, if I have a polynomial, like piece of cake, write the second order. Okay, so that means only go out to when your derivative has an x squared. I can do that. So the second Taylor approximation for f prime is going to be, well, the derivative of this thing, let me highlight it. The derivative of this thing, the derivative of 7 would be 0. The derivative of -3 times x minus 4 is just -3. The derivative of 5 times x minus 4 squared is 10 times x minus 4. And the derivative of -2 times x minus 4 cubed is going to be -6 times x minus 4 to the second. And then it says approximate f prime of 4.3. I just don't feel like doing that, but you'd plug in 4.3. Part C, we did these before. Since I'm maintaining my center, what we're really going to do here is we're going to take the antiderivative and maintain the center and ignore the plus C. Okay, so I'm going to take the antiderivative of this blue line here. Okay, so the antiderivative of 7 would typically be 7x, but x isn't centered at 4. X minus 4 is. So the antiderivative of 7 is 7x minus 4. The antiderivative of -3 times x minus 4 would be -3 over 2 x minus 4 squared. Now I want the fourth order, which means I need to go to the fourth degree. I meant to put a plus there. So then my antiderivative of 5 times x minus 4 squared is 5/3 x minus 4 cubed. And then -2/4 x minus 4 to the fourth. And I'm not going to take the antiderivative of the last one because they told me fourth order. Okay. And then last but not least, it says, can the exact value of f of 3 be determined from the information given? Well, this is centered at x equals 4, and I only have the fourth degree, which means I'm estimating it around 4. At 4, I know the exact value. That's not a problem. It touches it at 4. But anything beyond 4 isn't going to be perfect. So, can the exact value be shown? No, because this is only 5 terms of the series, and it's centered at x equals 4, not x equals 3. I hope that made a little bit of sense. Maybe it did, maybe it didn't, but you're learning things. Okay. Do I have any other jokes? The only other joke, do I have a joke? I gotta think. Hang on, I'm gonna pause you while I think. Oh no, I can't pause. No, I got nothing. I'll give you two jokes next time. Okay.